Once again, we have another problem in which we're going to be looking at the Lewis dot structures, come up with both the electron and molecular geometries, as well as the hybridization. We have 4 compounds here. So we have carbon diselenide, we have sulfur dioxide, we have formaldehyde, and then we have the ammonium cation. So let's get started. So we start with the carbon diselenide, and when we look at that one, if we count the number of electrons, there's going to be 4 electrons for carbon. Each selenium is going to have 6, so 2 times 6 is 12 plus 4 is going to be 16 electrons we have to account for. Now carbon is going to be our central atom. It's going to be double bonded to the seleniums. As such, we fill in the lone pair of electrons. So now here's, oops, forgot the double bond there, sorry. There's 8 electrons here, 8 electrons there, so that's going to be the Lewis dot structure. So the carbon is going to be double bonded twice to each selenium. The electron domain, or the electron pair geometry, is going to be linear. Now there are no lone pairs on the carbon, so this will be linear as well. Now because this is a linear molecule, the hybridization of the carbon is going to be sp. So we're looking at the hybridization of the central atom here. Now there's a couple ways you can come up with sp. You can either identify that this is going to be linear, and you can come up with it that way, or you can also notice that the carbon has 2 things bonded to it, so it has to have 2 orbitals. So if there's an s and a p, that's going to give you 2 hybrid orbitals. So here will be used up a hybrid orbital, here will be another used up hybrid orbital. If we look at sulfur dioxide, so the sulfur is going to have 6 valence electrons, the oxygen is going to have 6 valence electrons, so 3 times 6 is going to give us 18 electrons. And so the sulfur is going to be the central atom, and it's going to be double bonded to each oxygen. And we start filling in the lone pairs on the oxygen. Here we have 8 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16. So we only have 16 valence electrons. We're missing 2, so we'll place those 2 onto the sulfur. Now, we can look at this, and what this will look like is this lone pair will take up a space such as this. And so if we want to look at the electron geometry, what we sort of have is we have something that's kind of trigonal planar. I didn't draw a very good triangle there, but we have something that's going to be trigonal planar. So that's going to be trigonal planar. The molecular geometry, we're not going to include that lone pair, and what's going to happen is it's going to force the oxygens to be down. So this is going to be in a bent configuration. Now, to come up with the hybridization on this, once again, we look at the electron geometry and we see that it's trigonal planar, and anything that's going to be trigonal planar is going to have an sp2 hybridization. Now, because there's 2 p's and 1 s's, that means we're going to be making 3 hybrid orbitals. 1, 2, 3 things are attached to the sulfur. Now, even though that lone pair is not bonding, it still counts as an electron pair. It still counts as something coming off the central atom. Not necessarily bonded, but it is an entity coming off that central atom. And so here will be an sp2, sp2, sp2. So it's going to be an sp2 hybridization occurring. Now for formaldehyde, carbon's going to have 4, oxygen's going to have 6, each hydrogen is going to have 1, so we have 12 electrons we have to account for. And so this molecule is formaldehyde. The central atom is going to be carbon, and it will be double bonded to an oxygen and then single bonded to each hydrogen. And so if we count the number of electrons, here we have 2, 4, 6, 8, 10, 12. So now we have 12 valence electrons. Now this is going to be trigonal planar, so I'll try to draw this a little bit better. So that's going to be a trigonal planar molecule. And there are no lone pairs on the carbon, on the central atom, so therefore this is trigonal planar, as well as the molecular geometry is trigonal planar. Now, since it is going to be trigonal planar, the hybridization of the molecule is going to be sp2. It'll be sp2 as well. Now we get to ammonium, or the ammonium cation. We count the number of valence electrons. Each nitrogen has 5. Each hydrogen has 1, so that's going to give us 9. But we have a +1 here, which means it's going to lose an electron. So this has 8 valence electrons. Nitrogen is going to be the central atom. And so that is going to be our ammonia cation. It is going to be tetrahedral, will be the electron geometry. Now, because there are no lone pairs on the nitrogen, this is going to be tetrahedral as well. And once again, how do you come up with the hybridization on this? Well, once again, we can either recognize that tetrahedral, anything that's tetrahedral is going to be sp4, or, I'm sorry, not sp4, sp3, I can't count. It's going to be sp3. So there's one s, 3 p's, that gives us 4 hybrid orbitals. And on the nitrogen, there's 1, 2, 3, 4. There's 4 things bonded to it. And then, so the nitrogen is going to be an sp3 hybrid orbital. I know in the notes what I've done is I show you the genesis of how these hybridizations come about. And you can do that. You can fill in the boxes, you can fill in the s's, you can fill in the p's, you can move an s into a p. And that's not always intuitive. It's not the easiest. I typically find out that in order to do the hybridization or to determine the hybridization of a particular atom or a particular molecule, it's much easier to go and look at the electron geometry of it and then recognize if it's linear, it's going to be sp. If it's going to be trigonal planar, it's going to be sp2. If it's going to be tetrahedral, then the hybridization is going to be sp3. If it's trigonal bipyramidal, then you have sp3d. If it's going to be octahedral, you have sp3d2. I personally find figuring out the hybridization much easier once I know the geometry, or just count the number of bonding entities to the central atom. That's another way in order to determine a hybridization. If you have any questions on this, please ask.